number 7. Number 7 is another dilution problem, but it does get a little more complicated. We're going to go through this here, and hopefully you won't get lost in the forest of the trees. I'll go ahead and read it. So number 7, it says a chemist makes a stock solution of sodium hydroxide by dissolving 950 grams in enough water to make 2.0 liters of solution. If later on he wants to use this stock solution to make 100 mils of a 0.10 molar sodium hydroxide solution, what would he need to do? Well, gosh, let's see, what did they give us? They told us he originally made a stock solution. I'm going to try to bring my book over here so I can get in front of the camera while I'm reading it. Alright, so it said he originally had, he used 950 grams, number 7, he used 950 grams of NaOH to make a stock solution, and that stock solution was 2 liters. 2-liter stock solution. Right, so he took 950 grams, here's my beaker, and he put 950 grams of sodium hydroxide into it, and into that he poured 2 liters of water, 2 liters of water. This eventually is sodium hydroxide dissolved. It's an ionic bond. It dissolves. It's actually exothermic too. It releases a bunch of heat. Right, so it dissolves and releases a bunch of heat, and this 2-liter resulting 2-liter solution is going to be used later on to make that 0.10 molar solution. So how do we go about figuring this out? We know it's going to be a dilution problem. Because it's a dilution problem, it's going to be M1 V1 equals M2 V2, right? The molar concentration originally times the volume of the original is going to be equal to the molar concentration of the dilution times the volume of the dilution. But what do we got? We know what the original liters were, right? 2 liters originally of a 950 gram stock solution. What do we need? We need this. And you may think that this volume here is actually this volume here, but it is not. Don't be tricked by that. Right? Remember, whenever we do a dilution problem like this, when we're trying to make another stock solution from a given stock solution, it's always this original stock solution that we need to figure out how much volume of it do we need in order to make the volume of the dilution at the molarity that we want. Alright, so typically in 95% of these dilution problems, it's always going to be this V that we're solving for. Alright, in the chemistry lab it is always this V you're solving for. Because you're always trying to make another stock solution from a primary stock solution. You can't do it the other way around. I can't have a diluted stock solution and try to make a concentrated stock solution. I can't go from, say, a 10 molar solution and try to dilute it to make it 15 molar. It just can't happen. Right? You can only step down in molarities. You can't concentrate this. The only way you can go from 10 molar to 15 molar is by adding more sodium hydroxide. You're never going to be able to adjust the volume to come up with that. And you can argue that and say, well, I could boil some of the water off. Yeah, okay, yeah. You could boil some of the water off, but that would be totally incorrect as far as analytical procedure to do in order to come up with a correct molarity. You'd just be guessing about how much vapor you actually took out into the air. Alright, so like I said, 95% of the times you're looking for this V1. You're trying to figure out how many milliliters of this original stock solution do I need in order to make the volume and molarity of my new stock solution. And this is incidentally the way chemistry labs save a ton of money. They take this and they buy a really concentrated solution at halfway decent price, and then they make tons of other stock solutions from this. So from this one standard, which may cost $200, they can make buku number of standards from it, because water's cheap, right? Water's cheap. Getting the stock solution is the expensive stuff. So you can take your stock solution and dilute it millions of times and come up with all kinds of different standards, all different concentrations of standards. All right, so what are they doing to us here? Well, what is molarity, right? What is molarity? What's the definition of that? That is equal to moles over what? Over liters. So what did these clever people do? They gave us the components of this. They didn't actually give us the molarity. So we're going to have to take this information that they gave us to calculate our molarity, and then once we have the molarity, then we can do that. So they're just throwing an extra step in it from problem 6. So how are we going to do this? Oh my gosh, this is like almost a mole-to-mole ratio. We have 950 grams of NaOH. Oh yes, oh yeah, it looks very familiar. How many grams of NaOH are in 1 mole of NaOH? I don't know, let me look at my paper here and see what So it's 40 grams of NaOH are in 1 mole of NaOH. You multiply that out and you should come up with 23.75 moles. 23.75 moles. But are we done there? No, because that's moles. That's just in moles, but we want it to be in molarity. That's just the top part of this equation we just figured out. What's this? How many liters did we have? Oh, we had 2 liters. So, we got to go 23.75 moles, and we're going to divide that by 2 liters, and that's going to give us our molarity. And that's equal to, it looks like about 11.9. 11.9 capital M NaOH. Now, look, we have this, we got that, we don't know this. Do we know this? M1, M2, V2? What did they ask us to do? I don't know, let me see. They wanted us to find 100 mils of a 0.10 molar NaOH. All right, so this is M2V2. M2V2, so we're just going to plug this in. We know this is M1, right? So M1, I hope you can see this, 11.9 times X, V1 is equal to 100, no, M2 is 0.10 molar times 100 mils, and you should come out with 0.84 mils. Right, so it takes 0.84 milliliters of this original stock solution diluted to 100 mils to give me that molar concentration, 0.10. So I'm going to take 0.84, I'm going to use my pipettes that we used last week, and I'm going to measure out 0.84 milliliters of 0.84 mils. Very small amount, but they make pipettes that measure that accurately. Right, I'm going to measure out 0.84 mils, put it in my volumetric flask. All right, so here's my pipette. I'm going to drop in 0.84 mils, and then pour a bunch of water in there until I get it up to the line, the meniscus below the line, and that's going to give me exactly this solution. Easy peasy? Oh yeah, you just got to be able to recognize that first it's a dilution problem. It's clearly a dilution problem. What do I need to do a dilution problem? I need molarity and I need volume. You should have recognized, well, maybe not immediately, but after you scratched your head and said, hey, they didn't give me any molarity, but they gave me what molarity is made up of. They gave me 950 grams with my grams. I can calculate moles. With my moles, I can divide it by my liters, come up with molarity, and then plug and chug it. Clear like mud? All right. And there it is down there, 0.84, 0.84 mils.